Welcome to Mathematical Analysis. Today we are going to explore a fascinating and highly accurate method for measuring rates of change, known as central differences. If you have ever wondered how computers simulate weather patterns or predict stock market trends without doing exact calculus by hand, this is the secret. Let us dive in and uncover how it works. Now that we know our topic, let us build some intuition. Imagine you are hiking up a mountain and want to know the exact steepness of the ground right beneath your feet. You could measure the height one step ahead, which is a forward difference, or one step behind, a backward difference. But both of these are biased because they only look in one direction. A much better approach is to look half a step forward and half a step backward. By drawing an imaginary line between these two symmetrically placed points, we cancel out the directional bias. This perfect symmetry is why central differences are so incredibly powerful. Building on that hiking analogy, let us look at the mathematical formula. The central difference operator is denoted by the lowercase Greek letter delta. It instructs us to take a symmetric difference. We evaluate the function half a step forward at x plus h over 2 and subtract the value half a step backward at x minus h over 2. The variable h represents our step size, which is the physical distance between our data points. As this step size decreases, our 2 points get closer together and our approximation of the true slope becomes much more accurate. While the half-step formula is conceptually perfect, we often need to adapt this method to use full steps for practical calculations, like finding the first derivative. The first derivative represents the exact rate of change. By using a full step forward and a full step backward, we maintain that beautiful symmetry. Because of this symmetry, the largest error terms mathematically cancel each other out. This leaves us with an error of order h squared, which is significantly smaller than the error in one-sided differences. Let us see the formula that makes this happen. Here is the central difference formula for the first derivative using full steps. We take the function value one full step forward, subtract the value one full step backward, and divide by 2h, which is the total distance between those 2 points. Notice the error term at the end? It contains h squared. Because our step size h is usually a very small fraction, squaring it makes the error incredibly small. For instance, if h is 0.1, h squared is 0.01. This is a massive improvement over one-sided methods. Let us apply this to a real example. Before we prove why this works, let us see this formula in action with a concrete example. Suppose we have the function f of x equals x cubed, and we want to find the first derivative at the point x equals 2, using a step size of 0.1. First, we identify our forward and backward points. One step forward from 2 is 2.1. One step backward is 1.9. The total distance between these points, our denominator, is 2 times 0.1, which gives us 0.2. We have set up our values, so let us calculate the final result. Continuing with our calculation, we need the function values at our forward and backward points. Cubing 2.1 gives 9.261. Cubing 1.9 gives 6.859. We substitute these into our numerator and subtract, finding a total change of 2.402 over our interval. Finally, we divide by 0.2, which gives us 12.01. If we used standard calculus, the exact derivative of x cubed at x equals 2 is exactly 12. Our approximation is incredibly close, proving how accurate this method is. Now that we have successfully used the formula, let us understand exactly where it comes from conceptually. To prove this, we use Taylor series expansions, which are mathematical tools that let us express a function's value at a nearby point by using its derivatives at the current point. We write out the infinite Taylor series for one full step forward and one full step backward. Notice carefully what happens in the backward expansion. Because we replace every h with negative h, all the terms with odd powers of h become negative, while the even powers remain positive. This alternating sign pattern is the crucial key to isolating our first derivative in the next step. Continuing our proof, we will now subtract the backward expansion from the forward expansion. When we do this, something mathematically beautiful happens. The original function terms cancel out completely. The second derivative terms, which contain h squared, also cancel out perfectly because they have the exact same sign in both equations. Meanwhile, the first derivative terms add together to give 2h times f prime of x. To finish the derivation, we simply divide the entire equation by 2h. This isolates the first derivative and leaves us with our central difference formula, mathematically proving exactly why the error shrinks to order h squared. To truly cement this idea, let us look at it visually. On this graph, the blue curve is our function. The green line represents the exact slope, the true derivative, at our target point x. The red line is our central difference approximation, drawn by connecting the point one step backward to the point one step forward. Notice how the red secant line is almost perfectly parallel to the green tangent line. By straddling the target point symmetrically, the central difference captures the true trajectory of the curve far better than looking only forward or backward. This brings us to another powerful application. The central difference method is not just for the first derivative. It is extremely common to use it for the second derivative as well. While the first derivative measures slope, the second derivative measures curvature, telling us how fast the slope itself is changing. To find this, we return to our Taylor series expansions. But this time, instead of subtracting them, we will add the forward and backward expansions together. This clever trick will cancel out the odd derivatives and isolate the second derivative. Here is the resulting formula for the second derivative. To use it, you take the function value one step forward, add the function value one step backward, and then subtract twice the function value at your current central point. Finally, you divide the whole thing by the step size squared. Just like our first derivative formula, the error here is also of order h squared, making it highly accurate. This specific formula is the absolute backbone of solving complex physics problems on computers, like simulating heat flow or wave propagation. Let us see this second derivative formula in action with a slightly harder example. Imagine we are analyzing a wave, represented by the function f of x equals sine of x. We want to find the second derivative at 1 radian, using a step size of 0.1. First, we evaluate the sine function at our 3 required points: the forward step at 1.1, the central point at exactly 1, and the backward step at 0.9. Using a calculator set to radians, we round these values to 4 decimal places to set up our equation. Continuing our calculation, we substitute these sine values into our formula. We multiply the central value by 2, giving 1.6830. Combining the numbers in the numerator yields negative 0.0085. This negative number makes perfect sense because a sine wave is curving downwards at 1 radian. Finally, we divide by our denominator 0.01, which gives a final approximation of negative 0.85. The exact calculus answer is negative 0.8415, showing our numerical method is exceptionally accurate. Now that we have used the second derivative formula, let us quickly prove where it comes from. As mentioned earlier, we take the forward and backward Taylor series expansions, but this time we add them together instead of subtracting. When we add them, the terms with odd powers of h, like the first and third derivatives, completely cancel out. We are left with twice the original function and the even derivatives. By simply subtracting 2f of x from both sides and dividing by h squared, we isolate the second derivative. This elegant algebraic manipulation is exactly what makes complex computational physics possible on modern computers. So, we have proven that these formulas work beautifully. This brings us to a practical problem. The basic central difference operator requires us to evaluate functions at half steps. But in real-world data, like daily stock prices or daily temperatures, we only have measurements at whole steps. We do not have data for day 1.5. To fix this, mathematicians introduced the average operator, denoted by the Greek letter mu. It acts as a bridge, allowing us to enjoy the high accuracy of central differences without actually needing half-step data points. Here is the formula for the average operator. It is very intuitive. It simply takes the function value half a step forward, adds the function value half a step backward, and divides by 2 to find the middle ground. By pairing the central difference operator with this average operator, we can build advanced interpolation formulas that only require data at whole steps. This combination is essential for applying these highly accurate mathematical concepts to everyday discrete data sets. We have covered a lot of ground today. Remember the three most important ideas. First, central differences achieve incredible accuracy by looking symmetrically ahead and behind, which mathematically cancels out large error terms. Second, whether you are calculating the first derivative for slope or the second derivative for curvature, these formulas are the foundation of modern computational science. Finally, the average operator allows us to apply these continuous concepts to discrete, real-world data. You now understand the mechanics behind how computers solve complex calculus problems. Excellent work today.